Is my screen visible?
Yeah.
Okay. Yeah. Is the Google Colab notebook visible to you?
Yes, it's visible.
Okay. So
Yes.
I'll just share the link for this also. You can make a copy of it and try running some of the cells yourself.
Sure.
And
So
okay.
nice
So I think
column.
yeah. So it's Colab, and the interesting part was you could also do some amount of vibe coding with Colab, so which is actually very helpful in terms of boosting your productivity.
Very nice. Very
And
nice.
so okay. So
Some
I'll
of
just
these things also maybe helpful for our contests folks, right? So
yes.
maybe this could be used to, you could give them this tutorial and then give them some challenge problems, etc., right?
Yeah.
Which even small test things, and then if they have, they can sort of go up the scale of capability, and then maybe you can give them some challenge, larger challenges in the which they can go after. Okay,
Sure.
please go ahead.
Yeah.
Thank you.
And so I think in the last, I think we also have another mode which is called the Dhyuti talks. And in the Dhyuti talk, we had kind of discussed what pins were. And so this time, just happy to introduce walkthroughs, where we're going to deep dive into different SciML algorithms and paradigms.
Mhm.
And this is the first one. We want to look at pins, different relevant inverse problems. I'm not very fond of pins for forward problems. I'll explain what forward and inverse problems are, the difference between these two. And also, at least for this walkthrough purpose, to be able to cover different examples, I think we'll be looking at 1D analogs of real life examples across different domains. And and the other thing is, we had looked at, yeah. So firstly, like if you were to consider any given system, a physical system, and associated data. So there are ways to go from system to data and data to system. So when you go from system to data given certain parameters, it becomes a forward problem. And when you, let's say you have some data, partially observed data, fully observed data, and you want to discover what the underlying system is, that's an inverse problem. And typical inverse problems involve some sort of design optimization, predictive modeling, missing or hidden physics modeling, automated physics discovery, and optimal flow control. So these are some really nice review papers which I can also share separately offline. And so what are pins, right? So now let's say a very easy way to build intuition, just a recap of what we did in the talk, but to be more complete. So let's say if you were to have a person wanting to climb Mount Everest, and there is a particular distance he has to travel linearly and then climb a hill. And so there's some sort of physics involved, like here he's going, there's no elevation, so the amount of energy expended is lesser, whereas when he has to climb there's a lot more energy that he has to expend, so there are different physics that come into play. So let's say some key factors to consider are how much distance he has to cover and how much time can he spare to climb the entire uh, mountain, right? Now, however, there are additional factors that would come into play, which is pretty much governed by the physics of this problem, which is his stamina, the strength, the oxygen levels, temperature variations, and etc. However, there are ways to simplify this to just consider that this is a very ideal human being, and it is just any parameter that's going to play a role is just the gravity and nothing else, and the distance, right? So that is one way to simplify the problem, and then later add on multiple layers of complexities. So now, if you were to look at how do you bring this into a pin framework, is to think of it this way. So where let's say you have your input coordinates, that is your space and time, your spatial location, your lat long location, and time t, and then there is a neural network backbone n here, which is a function of your input coordinates and some unknown parameters which you want to calibrate through the learning process. Now this backbone can be anything. It could be a feed forward neural network, it could be a convolution neural network, it could be any backbone that is out there, any modern architecture that you, even transformers for that matter, it could be any architecture. But the only thing which makes it physics informed is that when you have the outputs of this network, there is a following block of automatic differentiation or even discrete differentiation to ensure that you, along with having labeled database constraints, you also have some boundary conditions or initial conditions, or you bring in additional physics-based constraints into the problem, which is some prior assumptions of how you want to model your entire governing system. So this is how a PIN is typically set up. So there is an input coordinate, there is a model backbone, there is an output, and output then goes through certain functions which lead to different loss components. One is the label data, then you have your boundary condition or initial conditions, then you have your PD or governing equation residuals, which essentially embed your physics into the system. Now, having said this, at least for the walkthrough purpose, it's impossible to consider a very large real life example. So in order to simplify things, we'll be looking at 1D analogs for different problems. So before that, an overview is that a standard PIN. So PIN is basically a class of neural networks with physics-based constraints. It kind of bridges your ML, your data-driven models, and the physical reality. And the seminal paper which made it famous was Maziar Raizi's paper in 2019 from Professor Karniadakis' group in Brown University. But it traces its history all the way back to I.E. Lagares, who had published the first paper on how you could use artificial neural networks to approximate PD solutions, and he had compared it with traditional finite element method. And now here you can basically have a standard PIN which is continuous in space-time, or you could have other different neural network backbones which could be also continuous in space-time, or continuous in space but discrete in time, or discrete in space-time, both, right? So it could be a bit combinatorial here. The major masala that makes it physics informed are the physics constraints which embed your ODEs, PDEs, or some sort of algebraic equations, the constitutive laws, or embed additional symmetries of the underlying system into the model. And you obviously have the database constraints, which are your observation data or simulation data, partially or fully observed cases, or your boundary conditions, initial conditions, and you have your system parameters as well. So in certain cases, which we will actually consider moving forward, is what if you were to infer a system parameter given some partially observed data, right? So which becomes an inverse problem. So input, just to revise the flow, input coordinates, then there's a feed-forward neural network. At least for this purpose, we're going to look at only feed-forward neural network, no other specialized backbones. Feed-forward neural network, there are going to be some outputs which go through the automatic differentiation pipeline. Again, you compute your data-driven losses, you also compute your physics-based losses, which in case of fluid dynamics, they're often your continuity and momentum conservation equations. In case of electromagnetism, they're going to be your Maxwell's equations. If it's climate, it's going to be your entire Earth system model or your ocean models. And along with that, you're going to have your carbon dioxide forcing and sea surface temperature forcing, etc. And then if it is traffic flow problems, you again have a set of OD optimal flow or optimal transport equations which govern traffic flow. So you could have varied domains in which a PIN can be applied for. It all matters on what your inputs, outputs are, how you're going to actually model the system, and how are you going to use this automatic differentiation box to get to those constraints and enforce them through another loss component. And the combination of this, a weighted combination of this in some cases, is what you're going to use and finally optimize to calibrate the parameters of this neural network. The key benefit of PINs so far have been that they work really well for spatiotemporal function approximation given limited and sparse data. And the best part of a PIN here, at least in the feed-forward neural network setup, is that your collocation points or your temporal spatial coordinates can be sampled from anywhere in any arbitrary domain. So it doesn't have to be of a specific shape or a structured format. So it could be from an unstructured grid, structured grid, any randomly distributed grid, set of collocation points as well.
So just a couple of questions, if it's good to ask now, or
Yeah. Please go ahead. Like, you can keep it as
so
interactive as possible.
sure. These are very basic questions. It's like I'm not. So one of the first questions is that so many of us are familiar with the standard neural network, no, like the inputs, the hidden layers, the outputs, and then the weights, biases, and all of that. I think it's you also. I think have it embedded in here, and then also the loss functions and a few other things, sigmoid and all of those also we are familiar with. So first wanted to just understand at a very high level how does so what is the modification happening to a standard neural network that like pins or on top of that what you're trying to do. That is one thing. And the second thing is, I think the XYT, I think for this example you're providing, but I think that can be any other variable also.
Yeah.
Like that can be like which govern, I mean, like formula physics and
Correct.
things. So that's
Yeah.
one example I'm guessing for
Yeah.
this. Okay. So it is the first example, first part. If you can just like you can, there's another feed forward part, but then like how what
Sure.
some level clarity would just be.
Sure. I think it's a very well timed question, because when we go to the implementation, it becomes even clearer as to how the simple feed forward neural networks becomes physics informed, right? So one is the first thing about pins that they're very easy to implement. At least now it should become pretty much textbook problems, right? So you have, let's say you have this function here which basically defines your neural net, and this neural net could be a feed forward neural network, some n hidden layers and some h hidden layers and n hidden neurons, right? It takes in the concatenated input of time and spatial coordinate, and there are weights and biases of the neural network, and it returns the function that is u, right? So now what makes it physics informed is that when it passes through this function here, so this takes in the spatial coordinates, gets the u function from here, and then computes the gradients of this function with respect to the input coordinates. So it basically gets the first derivative of u with respect to time, space, and second derivative of this function with respect to space, and then combines them to, let's say you have this advection diffusion equation here, like first derivative of time, then this convective term here, u dou u by dou x, and then the diffusion term here. So when it passes through this f is basically your residual. So ideally, if the physical law is conserved, this term should be 0. And however, when you're actually initializing the network, this term need not necessarily be 0. So with your optimizer, you would want to bring it as close to 0 as possible. And that is what you do. And this becomes your physics loss, or your physics residual loss. Does that answer your question? Like,
Yes. I think at least I'm somehow getting an idea now. So I think like Professor Suresh, yeah.
Thank you. So, Dr. Sundar, kind of just I have just one question related to this. Like once we are adding this PD loss, initial condition loss, and boundary condition loss, so in neural network we have this kind of this power comes from this universal approximation theorem.
yes.
But when we are adding this extra automate like auto grade and then adding this PD constraints like as a residual and trying to minimize, how we are kind of making sure that this kind of universal approximation is still valid after inclusion pin.
Okay, that's actually a very involved question, to be honest. So there have been enough some theoretical error estimate related work, which also talk about how pins are also good function approximators, and especially in a limited or sparse data scenario. Like when you have very sparse data, if you were to train a purely data driven network without the physics based laws, you would not be able to recover the original target function, right? Let's say if you have 100% data, you only train on like 5% data and 95% of it is left out for testing. Your model is not going to do well if it is purely data driven. However, the physics based constraint actually tends to do well in this case, because it brings in additional constraints which kind of balances for the missing data. yeah, does this partially answer your question? Might perhaps does not theoretically give you a closure, but I could perhaps
Yeah.
share some papers which are relevant to this question as well after the session.
No, thank you.
Yeah. So now we could actually look at the walkthrough. So for the setup, you basically need a data set. You need the model architecture, its parameters, the loss function and the validation metrics you're considering, the optimizer you want to choose, and evaluation monitoring pipeline. But for this setup, we'll keep it as simple as possible and try to build intuition on how a simple feed-forward neural network itself can be the same core code can be repurposed for different physics, which has a lot of power in terms of flexibility. So I'll share this Google Colab link with all of you again. Yeah, are you able to access the Colab notebook?
Yes, access, and I just made a copy. So, Professor Dubey, you can also make a copy. It will be helpful so that the original one is still there. And the copy will go to your own Google Drive. In that way, like you can also make further edits on top of that.
So this walkthrough. I gave it a bit of thought, and I understood that in a walkthrough, especially for this walkthrough, we have been getting audience from different domains, and I think the broader purpose was to build intuition on how pins are broadly applicable, right? So let's say if you come, whether you come from fluid dynamics, material science, nonlinear dynamics, quant finance, computational biology, geospatial, climate sciences, electromagnetics, or doing field inversion studies, or EV and engineering design, the idea is to, through this book, at least I try to find some 1D ODE or ordinary differential equation or partial differential equation analogs that you can quickly set your pins up for, and to understand how it bridges physics and data. And most of these 1D analogs tend to have a closed form or analytical solution that we can visualize and later use to validate how well the pin tends to do. And just a disclaimer, most of these equations here are pretty much linear, so it's not a wise idea to apply pins for linear problems. There are other algorithms which can be used, and they are better for linear problems, such as physics informed extreme learning machines, where you only have to learn a last layer and you have random basis functions that are generated. To know more, I can possibly share the reference towards the end of this session. But pins are generally useful for nonlinear problems, and where you have some limited data and you want to invert and obtain the system parameters or recover certain missing observations. So let's say we have the material science. You have, let's say you want to, given some measurements of temperature, you want to identify what is the conductivity, thermal conductivity of the material. Then you could use this heat diffusion equation to model that problem. Then for fluid problem, on a 1D analog of the Navier-Stokes equation would be showing the nonlinear advection diffusion equation. Then nonlinear dynamics, a very classical example is your Duffing oscillator, which is basically a simplification of largely oscillating pendulum. And investment banking, let's say you have option pricing that you have to determine, you have the Black-Scholes equation. Then computational biology, how do you model population growth and its saturation? Then you have graph theory on how do you show diffusion on a graph. Then geospatial, you have, again, when you have scalars like pollutants, aerosols or something, how do you model their spread in the atmosphere? And electromagnetics, let's say field propagation. and 1D analog of it is again a second order equation, partial differential equation. Then you have EV domain, where you try to have a simple analog is your RC circuit, charge discharge model for EV systems, for your battery packs, let's say. Then you have climate modeling, you try to look at what is the global mean energy balance for Earth's temperature. Then engineering system, you have elastic deformation of a beam bending equation, and so on. So the idea of this entire Google Colab notebook is to find suitable examples from your respective domains, and feel free to modify the loss functions, or you might only have to modify the loss function and your data generator. Rest all should work as it is.
Yeah, this is very nice. Like, thanks, Rahul. So because you put in all of the different fields together in one single thing, no? Like, so that's very useful to know how. I mean, all of these are basically governed by either ODEs and PDEs.
Yeah.
So it's a good understanding of this. Is like, so you just showed these ODEs and PDEs now. I think previously we used to do it using like finite element methods, finite different methods, and so on.
Correct.
Now it's like you're going to generate the data for all of this,
Correct.
and that data is going to be like the input, and the neural network is going to try and solve this using these data points, and it's going to basically learn by itself what these governing equations are. Something like that is a good understanding of the whole scenario. Like,
okay, so just a correction. So if you since you mentioned finite element method or any of these approximation algorithms, so the way they work is, you, at least in finite element method, you assume some sort of an ansatz or some sort of a shape function. So let's say if this is the variable that I want to solve for, I can clearly say by looking at this equation that u is a function of x and t, correct?
Yes.
So now x and t are the inputs to this function, correct? So now the solution of this PDE, u, which is u x of t, is a function, and the inputs to that are your spatiotemporal coordinates, so that you can, at any given time or space, time and spatial location, you would want to infer what your solution is or what your temperature is. Let's say in a given radiator of a car, or let's say if you were to look at bikes also, on the engine outer side you have these fins which tend to radiate away the heat, and also convective heat transfer happens from the engine's outer side. You have these fins that are there, right, on a bike engine. So now if you were to put a thermometer at any given spatio-temporal location, any given location, the temperature is going to vary over time. So the input to this is also basically space-time, and you're going to measure the temperature at that given space-time location. So the neural network can be thought of as a measuring device, which takes in x and t as your, or spatio-temporal coordinates and time as inputs to this, and spits out the variable or your prognostic variable of interest. Like the variable here could be u, which is the solution of the PDE. Now, if u is the solution of the PDE, and if I model it in such a way that it is continuous in space and time, then I can actually compute these derivatives directly, right? By chain rule.
Yes, that's true. Yes.
Right. So once I do that, which is what the TF gradient or the example that I showed earlier was about.
Yes.
So once
Yes.
then I can basically, here there's an equal to sign, but if I were to bring it to the left hand side or bring this to the right hand side, I'm going to get this entire thing equal to 0.
Yes.
Which is what I would ideally have in a situation where the physics law is conserved.
Okay.
But in the initial stages of training, I am not going to have that to be 0, and I want to bring it close to 0. Now, what informs a PDE is, of course, the initial condition, boundary condition, if it's an initial boundary value problem. And if it's a boundary value problem, you only have the boundary condition. If it's an initial value problem like the Duffing oscillator, it is just the initial condition that are of interest, that are of importance.
Okay.
Right? And the other caveat that is important to understand is that now, along with having this physics knowledge, I have some partially observed data also. It's like I'm not asking the neural network to guess out of thin air and some initial constraints, but I'm also saying that, see, along the entire curve that you have over here, could possibly illustrate as Yeah, so along the entire function, I have some points in time and space where I have actually measured the solution, or I have some observations. So I'm saying that use these also as some additional information and try to.
You're showing that raw data here. I think
Yeah,
it
yeah,
came, but then
yeah, yeah. I'm creating one. Yes. Yeah, is it visible now?
yes, yes.
So now let's say this is my y coordinate, and then there is this is my time coordinate. Right, so this is my time coordinate, this is my spatial coordinate, and then I can have a curve something like this, right? So now what I'm saying here is this is my actual true solution or my analytical solution, and then or this is what I want to learn. However, what I have with me is just some partial observations here, and given this is also a boundary value problem, I'm going to have some constraint at the end point of this, or the extent of this entire domain, spatial domain as well. I'm saying that I'm going to have some sparse measurements like this, and there are scenarios where these observations themselves could be noisy, so you might actually be away from the true curve, right? So you're trying to still do some sort of line fitting here, but this line fitting happens with the help of your physics-based constraints, right? The ones that are outside of the true line are often your noisy observations. On the line are the actual observations. So you might encounter a scenario like this, right? So you want the PINN model to actually learn this, infer this solution alongside doing some additional tasks.
Okay.
Okay, so now
Okay.
yeah, so now we will go into some of these problem setups. So let's say we take this heat diffusion example. So we want to model heat diffusion along a rod. We take very simplistic domains. The domain extends from 0 to 1 in x direction, and in time it's again 0 to 1. The initial condition is at basically at time t is equal to 0 is basically a sinusoidal function with a period, half a period, and then you have boundary conditions such that you have homogeneous boundary conditions, and for this kind of a setup your analytical solution turns out to be this. So the applications typically are thermal conduction in solids, atomic diffusion, sintering, semiconductor doping, corrosion modeling. So this simple equation itself has a multitude of domains where it is heavily used, and so then again fluid dynamics setup, you have viscous. So I think like you can take your time and go through all these potential examples, how they are set up. For all of this, we have this data generator, which basically generates all your analytical solutions to these equations.
Oh, very nice. So you're saying that like you're not just doing one example, but you have given examples for all of those, is it?
Yeah, all of them. At least for this demo purpose, I've solved heat example, but I have the code set up for most of these cases. At least the data generator and loss function is what is left as an exercise for people to try it out for different domains that I have
Okay, sure. Got it. So the heat one is the what you have actually going through the rest of the code.
Yeah.
Okay, sure.
So here, once I have, so you have these analytical solutions. You can use any one of them to generate your target data.
Yeah, the reason why I was asking is Professor Dubey is from the atmospheric sciences, so I saw a few applications there.
Yes. So I think there's this climate modeling example, and also this geospatial sciences, like pollutant transport in a river, which is then this is
One
one.
more was there, I think. Yeah,
There's
one
another
more.
one. Yeah, this Earth's mean temperature over time, how it
Yeah.
evolves. Yeah, so this is.
Oh, sure.
Yeah.
Okay.
And so now we have this data generator functions, helper functions. So we basically generate a 1D grid.
Yeah.
And 1D grid in space, and again in time, again we divide it into
Yeah.
some 100 instances. It's not necessary that you have to. The best part about pins is you don't have to divide it at equal intervals. I mean, this is just for simplicity, but you don't have to divide your spatial domain and discretize your spatial domain and temporal domain into equal intervals. You can feel very free to select points which are closer. Let's say if in this function, for a network, it would possibly be very difficult to fit this curve, right? It's actually difficult to learn this curve as compared to the straight line, monotonous straight lines, right? So
Yes,
you might prefer to choose more sample points
yes.
that are closer to this location, right? You would choose more sample points here, right? So that you get better approximation of this. So that is one way.
So the way to kind of generate the points in maybe in that interval first, and then generate the other points in other intervals in a non-uniform way, something like that.
Yeah, you can have a non-uniform grid, so it need not
Yeah,
be a uniform grid. Yeah.
Okay.
So that's a caveat. That
But the example that you have here, it is uniform, no?
It is
looks
uniform.
like
Yeah, it is uniform.
Okay,
Yeah.
sure. Okay.
So then you can.
So what will be interesting is that, I mean, since you picked this very nice example, which you just showed, no?
Yeah.
Is that these are also solvable by standard simple like solvers, like even both linear, and then so it will be great to see how this example is wherein you bring in these physics constraints. Maybe in a future, like a continual thing we can do, how this physics constraint is actually helping than when you do it, say, using some very simple on some standard solver, which will just take either like a linear like pseudo inverse or any of those other regression based methods.
Yeah. So yes, absolutely. And in fact, if you were to use, there's a very clear problem here that you mentioned here, is that pins are generally underperforming for any forward problem, right? Which is when I say that I have a PDE, I have to solve it. Then pins actually underperform your traditional solvers for a given parametric instant. But however, when you have scenarios where you have some partial observations from experiments,
yes,
right, in such cases pins actually are very helpful, because it's just a single model, flexible, and then you get to, and now the optimizers have evolved, the weighting the entire architectures, more modern architectures have come up even in pins, and the loss formulations, how do you have to train, the training strategies have all evolved, sampling strategies have all evolved, and as a result you can get to performing very good error metrics, like, which are very satisfactory, and we can train the networks also quite fast. And there are some additional advantages as well, that once you train this model, it occupies very low memory, so you can and it is useful for real-time query, right? So which is why pins are fancy. And however, the pin that I'm going to show here is just a standard pin, so it might not be as performant as a CFD solver or this thing, but it is like the entry algorithm to scientific machine learning. So that's just one other caveat.
Sure.
Yeah. So here we have these helper functions.
No, I didn't mean a CFD solver, even a basic solver, no? Like so what in the example that you shown, like it's a simple, you can solve it using standard regression based methods and even other. So then I think the next step there will be like CFD solver, and then the next one step will be CFD.
Yeah, even for inverse problems, such a comparison is important.
Yes.
Important. I think that can be the next step, like even after this session.
Yeah.
Possibly. So now let's say, so I have defined the helper functions to synthetically generate this data, and so here is a nice widget, so I can actually do this. So what I can do is I can choose between equations and visualize their solutions and add some noise to the data and see how they get corrupted and so on, just to visualize how your data is going to be, how your target data is going to be. So in cases where you're working with partial observations, you might actually have this kind of noise in the data and some amount of, so this 0.09, this is about 9% noise in the data, and you're going to also have some missing patches here, so which is your typical scenario that you would encounter. And now here we will also have a helper function to, one is we have helper function to generate the data. You also have a helper function to store this data in some NumPy format. And then once you have this, you have to, I'm using PyTorch framework, so you need to have a way to prepare the data and convert them into tensors, torch tensors, and reshape
So,
them.
yeah, there's a very basic question. So can the previous one again? This is just to so that like basic understanding is always there. In the previous image you showed, no?
Yeah.
So wherein x and t are there. So and this is the heat equation as from the this is the differential equation that you had shown earlier in the first case.
Yeah.
Like where you had showed that you have x and t and you have defined x and t variables, and then you have the like in the top you showed the different ones. No, that is this.
So this is
So
a
what is
solution for the first equation that I showed, like just the heat equation or the diffusion equation that is over here.
okay?
Yeah, for a specific
Sorry.
value of d.
Yes, exactly. Yeah, so that's basically what. Yeah, just for completeness, no,
Yeah.
so that we kind of understand each and every minute details. Also, that's what. Okay, great.
Yeah. So now we.
So will this act as like a ground truth or so? Will this act as ground truth or observation?
Yeah, this will act as your
In the
ground
name.
truth. I mean,
Ground truth, right? Yes.
yeah, ground truth.
Okay.
So the
Okay.
other interesting thing to understand here is that the physics laws is actually a regularizer term. So in typical machine learning models, you have the data-driven laws. Along with that, you have regularizers, right? So you have this
Yes.
Tikhonov-based regularization, or you have the weight decay, etc.,
Lagrange
Lagrange
multipliers and other things.
multipliers and all, right? So similarly, you can think of PD residuals as an additional regularizer for the model, so that it is robust under noise.
Sure.
Yeah. So now, so this is my diffusion equation. I have the boundary condition, the analytical solution to it. Just a minute, there are a couple of notational changes.
So the boundary condition, initial conditions are also in some way like the physics constraints, right? Like normally, like okay. Because or else if they're not there, then you can. It's like no. It's like you can just generate any data. Like you can just fit the constraint is not there. So this is like the way of constraining.
Okay. And then you basically define these parameters. Then you define your domain size and create those grids in XT, and you basically create a mesh using NumPy. And then you have your true solution. Then you introduce a noise level just to corrupt your data a bit. So you have your true ground truth, and then you corrupt it with some noise level. You basically choose Gaussian distribution and scale it with a noise level here, and then corrupt the data. And then you also apply some amount of random masking so that you remove 20% of the data. I mean, you can go up to even 80% and just have a few 10% data and all. So now let's say, sorry, you only retain 20% of the data, you mask the rest. So now then you convert these data points, the xt and the ground truth, into the noisy ground truth into torch tensors. And so here is what the data set would look like once you corrupt it with noise and remove certain percentage of the data from.
Very nice, very nice.
And so now here is the main masala, which is the PINN model. So this is a simple feed-forward neural network, and in fact here it is just 4 layers: the input layer, 2 hidden layers, and the last layer. So in fact for these 2 hidden layers you can even derive things by hand. So that's one interesting thing about 2-layer networks. It's actually a shallow network, it's not a deep network. And then there's you basically initialize this network with nn.sequential, and you define your network architecture. Then you also additionally, in our case, we are trying to infer what this diffusivity of the model is, and which is why we have this d and k as learnable parameters. And the forward is basically a forward pass which concatenates your space and time together and then passes it through the network. And then you instantiate the model, and then you have your optimizers. Here I'm choosing ADAM optimizer, which is adaptive moment optimizer, which significantly improved upon the original stochastic gradient descent method. And for this optimizer you have to provide inputs where, like, say that the model parameters are what I'm going to optimize for. And in this case, when I say model.parameters, even this gets accounted for. And then you specify your learning rate. Here I have fixed the learning rate, but you could also choose a learning rate schedule and decay it based on how your loss improves or degrades. And then I have chosen 5,000 collocation points for physics residual. And then I basically randomly choose these x and t collocation points, with maximum value being 1. And the other thing is you have your observed data set. So you have your physics collocation points, your x and y t coordinates that you need to choose, and you also have your observed points where you have x, t, and u. So now once you have defined this, the next thing is to define your loss function. So which is where you have, this is the most important part here. So once you, let's say you get your model, it gives out an output. The other thing is you need to be able to compute the gradients with respect to your input coordinates t and x. So now you have the model x, you have the first derivative of time, first derivative of space. So we need to make a modification here. So getting back here. So this takes into account some sort of a convective term of the first derivative, which is not required because we are solving.
This is, just to understand, so like now I think I have a better understanding as you were just explaining the whole thing. Just like again for, so in a traditional like a feed like a backpropagation network, you'll do this fill part, then you'll backpropagate the error, and then you'll try to learn and so on, right? Like that's the usual one.
Yes.
So here you are computed the output.
Yeah.
And then you are, instead of backpropagating the error and doing that, but you are rather like you have the original differential equation, and you're like trying to compute the gradient from that part, and then trying to like put another like couple of more constraints, like the data driven constraints and the loss constraints, and then trying to do that, right, based on your first something like that.
So,
okay, very.
So to even make it clear, so let's say in a typical setup, right? Forget about PINN or any machine learning problem. You're going to get these kind of observations, right? The quality of observation can be determined by how close they are to the true solution and whether they are noisy or not, right? And on top of that, you also know something more about that system. You know the physics,
Yes.
right? So now you have data and you also have physics. But in the case why physics would be useful is where you have very sparse observations. I mean, you see here, like this is, let's say, just 10 observations for a curve that possibly requires 1000 to approximate, right? 1000 points to approximate. Now, if you had like 800, 500 grid observations, then you could just go ahead with data-driven model. You wouldn't even need a physics-based model, physics-informed loss. But in case where you have only tens of observations for a function that is quite complex, then you would need some additional constraints. So now where would you bring those constraints from? Is if you know the physics of the system, you bring those constraints also. So either ways, the backpropagation happens in order to train the model, but the number of lost terms, so it becomes a multi-objective optimization problem. So one objective is your data-driven loss, the other objective is your physics loss. So it tries to find a Pareto friend between these two. Is it clear now?
Yes. Absolutely.
Okay, so now we need a correction. So if you had noticed, you had asked a question that was very important. So are we solving the same equation? So we are now solving the same equation. So now it's a diffusion equation. There was a convective term earlier which I have removed now. So it is just the diffusion equation. So I don't need this first derivative of space. And I have defined my loss function, which basically gives me the model output at any given time and space x and t. And then I have the first derivative of time, the second derivative of space, right? So the thing about torch autograd or grad is at any given point it only calculates the first derivative, so you would have to do it twice. So you have to compute the first derivative of space and again pass it again as input, and you also have to define your coordinate with respect to which you are computing the derivative, and then you have this, and then you compose it to get your governing equation. Right, now let's train this model to obtain.
So when you're training this, both these losses are taken into account, no?
Correct. So you have this is your PD residual, right? So when I say
Yes.
loss, so you have your loss data that you compute, which is basically my mean squared error, and loss residual, which is the mean of the residual squared.
Yes.
Yeah. So it's just a squared L2 norm of my residual, and then I have the final loss, which is basically a weighted combination of this data loss and physics loss. So generally this loss weighting generally helps because you're trying to balance the contributions of both these loss components. So generally it is advised that you relax the physics loss weight as compared to your data loss. And again after this you basically do a backward pass, then you step your optimizer, and then you do this for some n number of epochs. Yeah, you can see that this would keep changing now. Oh wait, I can stop it. And for every, let's print every 10 epochs and see how it evolves. So you can see that the D value is actually increasing. So our expected true value is 0.05, and we had to give an initial guess. So we chose somewhere about 0.005. So the model has to learn, and so you also saw that we had this data which was 80% removed. So this is what we have, and we have an initial guess of what the system parameter could be, and moreover this is a noisy data set. So now with this we are trying to recover what the system parameter could be. So this is going to take a bit of time to get to where we want to, but you can see that it is actually slowly going up. Yeah. So this is the entire process. So you have your loss optimization. Along with this loss convergence, you also have this unknown system parameter that you're trying to infer. And what happens with this model is that it not just infers this unknown parameter of the system. Basically, for a given material, you have some measurements. Then you not just infer what the temperature of that material, what the thermal conductivity of that material is or diffusivity of the material is, but rather you are also able to infer the entire solution at any given space and time. So you might have only this data, but you would be able to reconstruct the whole solution sans noise, which is like the key advantage of this method. Okay, so this is going to take a bit of time. So let's do one thing. We'll just give a better guess to begin with. Let's say something like 0.1, and we'll give a learning rate of, okay, this seems fine. Same thing. Yeah, it's able to converge faster to okay. So the reason why you might see, okay, this is important to mention. So the reason why you might see that it is actually going, it is very close to 5 and then again drops off and then again trying to learn, right? So this could be because of two reasons. One is it's actually trying to fit and recover the data. So it has two things to do, right? One is it has to fit the data, which is your data loss. It has to minimize this loss. And apart from that, it has to also minimize your physics loss. So the more it does a better fit of your data, the closer you would be towards your physics, and also be able to recover the missing parameter. And the important thing is we have kept about 2% noise in the data. So this is going to take some time. So meanwhile, if you have any questions, let me know. Like, you can answer those meanwhile. Okay, let's just talk
So that
about.
kind of a lost surface is like.
Oh, you mean to say lost landscape of this?
Yes, yes, yes.
Oh yeah. So this will be a multi-dimensional lost landscape. So you would have to do some sort of 2D projection and then visualize it. So when you
Okay.
have any sort of, so this is actually a very nice paper by Gopakumar. So where he also points out that when you have data, some sparse data, your loss landscape becomes much more regular and easy to manage and train the model with. So this is a very nice informative paper on this. So I'll try to see if there is a very nice plot that we can discuss from this paper. So if you see here, so the no sparse data, I mean, this is a 2D projection of a very high dimensional loss landscape. So you should not mistake this entire thing for having a very sharp gradient. But let's say if you look at this, there seems to be some sort of a saddle point, and there seems to be multiple local minima. This is one local minima, there's one here, there's one here, and this is a global minima, let's say. Now, this is when there is no sparse data available at all. You're just training the network with pure physics-based constraints and boundary condition constraints. However, when you have even 1% sparse data, the loss landscape regularizes such a way that you have a very clear minima that the model has to go towards, right? So you're not going to settle on very suboptimal options, but rather you're going to go to something really good. At least this is a very high level overview of what Gopakumar talks about in this paper. And this is actually a very nice tool to visualize how your models are learning in general. So you could even construct these loss landscapes for PINNs, convolutional neural networks, diffusion models, name the architecture. You could construct these loss landscapes, and it's nothing but you have to have checkpoints of your model over training, and then concatenate all of them, flatten the weight vectors, then take a PCA of that entire time history. So you have to think about this weights evolving over time, and you basically take that entire time history of these weights and flattened weight vectors and take a PCA of that and project the entire set of checkpoints and the loss trajectory onto the top two PCA modes. Once you do that, then you basically construct a grid and estimate your losses over every grid on the axis of these two projected vectors, two top PCA vectors along these two. Considering them as axis, you basically construct a grid, you explore along this, and then compute the loss, and that is where you get these. The actual loss trajectory would be something like, let me see if I can annotate this. So the actual loss trajectory would be something like this, right? But the loss landscape would help you visualize what is the possible set of trajectories that the entire model can take depending on different initializations. So here in this case, you might actually settle down somewhere here, or you might start from somewhere here and then go here, and then, or you go from here and then you actually settle down here. But with
Very interesting.
Yeah, so they're very nice paper on loss landscape.
So where is Professor Gopakumar? Like,
I think he's from UK Atomic Energy Authority. So this is in 2022. I don't know where he is now, but let's see where this is now. Okay, so this has underpredicted it. It has just gone to 0.01 now. That's for maybe a lot more iterations it would get there, but perhaps let's not wait for it. Let's see how much of an underprediction this is. Yeah. Are you able to see the collab screen? Hello?
Yes. Yes.
Okay. Yeah. Now let's say we plot this. So when you're using a GPU, the constraint is that you have to ensure that your tensors, your model, everything is on the same device. Okay.
Yeah, that's where you do some two device, no CUDA two device or CUDA like the thing, so that two CPU, or else that's not available means it will go to CPU. Like.
So now one thing we need to check is what is this model device at the moment. So you hit model eval, then you actually do send it to CUDA, then you're done, and this should help ease out certain things. Yeah. So I'm basically plotting the analytical solution, the PINN prediction, and the error percentage. I mean, because we have under predicted diffusivity, you see some certain really high errors in this region, close to almost 80-70%. Then whereas here you see a decent, relatively much closer, like less than 20% errors. So obviously when you train the model for a longer time, you're going to get better results and better architecture, and all these things would certainly mean that you can train the network also faster. And given that this is a linear problem, PINN is also an overkill. It's just a illustrative example, but I wouldn't advise people to use PINNs ever for linear problems unless they go via the extreme learning machine route. So this is one nice paper. This is from Professor Balaji Srinivasan's group at IIT Madras. Yeah, the author is Vikas Dwivedi. This is a very nice way where, so in this, if you notice in PINNs, we had all the layers which it had to learn, right? So whereas here for physics inform extreme learning machine, the one thing that you do is, let's say you have, this is my network, I kind of freeze what these weights are. I just randomly initialize them, and I basically have all possible random basis functions, and then I try to find what should be the optimal linear combination of these in order to get to my solution. So this kind of a structure is very suitable for any linear PDE that you would like to solve, and also carry out differentiable programming or differentiable inverse problem solutions, and which is where this paper is also a very nice read. Apologize if I'm giving very fundamental and basic examples, but I think this is just to build intuition, and we can certainly evolve this whole thing into solving much more realistic and relevant problems. And this is just an educative example of how we could set up PINNs for certain problems. And I would like to close here and just leave you with one particular thing, which is to say, let's say, how do you extend this to different problems, right? We saw heat conduction example. Now, in case where you have Berzer's equation or Navier-Stokes analog, you want to infer what is the viscosity or the Reynolds number of the flow. Then you again have your collocation points, you have your observation data, and in experimental scenarios, you're going to mostly have particle image velocimetry measurements, snapshots, or you're going to have some sort of scalar, like let's say smoke or dye experiment. If you were to do, you have the concentration of that, and you could construct a transport equation from the transport of that scalar quantity. And with using that scalar quantity, it is possible to infer the velocity, pressure in the case of Navier-Stokes or fluid dynamics problem, and also infer the Reynolds number of the flow. and which is what is called hidden physics recovery or hidden physics modeling problem, which is a very interesting inverse problem to deal with. And then you have duffing oscillator, where let's say you want to infer what my damping coefficients and nonlinear stiffness parameters are. Given that I only know the linear stiffness parameter, how can I infer the damping and the nonlinear stiffness parameter for this equation? Interestingly, this is the only ODE that we have seen here. There is also OU process, which is a stochastic differential equation, and which is very similar, has some correlations with your Black-Scholes and your option pricing problem, and this is a nice analog of that. And you would want to infer what my k and theta parameters are, which is again, now the other last three problems are interesting, where let's say I have some measurements of u and I have what my d is, but I want to understand what my source function looks like. Then I just don't have to consider this to be a single parameter. Rather, I would model it as a neural network itself. And especially if the source itself is a function of space, then I can model a small neural network which is a function of space, and compose both this network and this U network together, and then optimize this combined physics laws. And so goes for this equation and the beam bending problem as well. And I wanted to, probably next time I think I could also show how all of this boilerplate code becomes easier with NVIDIA Physics Nemo kind of framework. So Physics Nemo is a very nice framework where you have predefined backbones for not just PINNs, but also all the way up to your foundational models for climate science, such as ForecastNet, and even foundational models across different science and engineering domains.
And even neural operators, no?
Yeah, neural operators.
Like,
yes. So all the way from
it's amazing that it has all the three.
Yeah, all the entire spectrum of algorithms that you can find in scientific machine learning. At least good percentage of them are being covered by Physics Nemo, and it's a very nice framework to begin with and explore the existing use cases that they have defined. And they also have nice examples.
So we can maybe do it this in a weekly format.
Yeah.
Again, because it would be very nice that, as much as possible in a weekly format.
Yeah.
Because what would be very nice, is that so most of the like online tutorials, papers, everything, they won't go into the details because you want to go and just show, okay, this is possible, kind of things.
Yeah.
And today, for the example, you went into great detail. Personally, I would go into even more detail.
Correct.
Because you can think of it as two ways, no? One is, yes, you're explaining the concept.
Yeah.
But you can also think of this as, this is going to be a repository wherein you are deep diving and you're actually both learning on the go, as well as once you put it online and other things, this is going to be a repository which maybe, we never know, at any point of time, anybody can even go back and use this. I myself have seen similar repositories online, which are really old. You can even think of there were used to be lectures from IIT Delhi, Professor S.C. Datta Roy, one of them, some amazing lectures on DSP, signals and systems, or even Gilbert Strang on linear algebra, or even Andrew Ng later on. And even there have been more recent ones which combine classical lectures as well as these codes, more recent ones are doing that. So it will be really good if we can, today, like how you went into detail, no? So maybe we can even go into the detail of showing the mesh, showing how the loss happens.
Right.
Professor Hani Farid from, there are two lectures that come up. One is Professor Hani Farid from Dartmouth, from UC Berkeley now, used to do those kinds of videos. And there's also one from Harvard. There is an applied mathematics or applied machine learning kind of lecture. Every concept is, you will have one supporting Jupyter Notebook, Colab or Jupyter Notebook, wherein very detailed, even simple things will be taken care of. So that way, when we go, you will have the basic ABCD to the most advanced things also. Things will be there. And that will be both for us a good learning resource as we go on the fly. Of course, the time we'll have to invest a little bit more, but this time what we invest will is like the multiplier effect that it will have in later point in time will be like much more significant.
Yeah.
And for future, anybody wants to refer also, they can refer it if at all. That's the those would be-
So how about this plan? Like, what? See, I think there is also this problem of actually getting into a rabbit hole of just one algorithm, right? How would we do this? So we actually have a cyclic process. Let's say we do pins now, then we do an operator learning approach, then we do diffusion models, then automated discovery, Bayesian optimization. We cover them in similar levels of, let's say, a first step to all of them, and then we again come back to pins. We revisit pins with a lot more rigor in terms of getting into the nitty gritty details of how do you even tune or make it very performant is one. Then also take a much better example which is more relevant and impactful. Along with it, we
Excellent,
also show
excellent.
that
Yeah.
we basically show the loss convergence, what kind of monitoring tools that you need and evaluation criteria that you need to set up for any given problem, right? So how do you do that? I think we can get back into the nitty gritty details once again, like in a cyclic format. So that
Oh
will
yeah,
be
that would be very nice actually. That's even better than the thing what I was saying, because you also get a high level overview of the first level of the different algorithms that are out there.
yeah.
And then when you go back, you also like refresh and then again go back. That's when the new ideas, new concepts, and new things will usually, well, all of them will arise. It may look like, yeah, that's actually even better suggestion. Professor Sarvesh, you have any suggestions or feedback or any, how was your, anything?
No. Actually, I'm very fascinated with like pins, and I kind of have just started using it again. So when I saw this, so I wanted to like learn and see. But this is actually good that mostly when I only do for atmospheric science related problems. But here we are discussing from many fields and all, so that kind of information, everything all together, might be very useful.
Firstly, thanks so much for attending, and this is a very encouraging feedback as well, right? I, so I'll make a note of it, and I'll also ensure that even in the upcoming sessions, I try to maintain the generality of these approaches, so anyone who attends can still make use of the content that's been presented. And I think we are like over time now, and
Yeah.
thank you so much for
Thank
spending your
thank
Friday
you.
night with us for this session.
Thank you very much, Rahul.
Thank you.
Bye.
Thanks, Professor Sarvesh. That's very nice. Okay.
Yeah.
Thanks, sir. Thanks,
Thanks
Rahul.
everyone. Yeah. Thank you.
Bye.